Okay, so we want to talk about differentiable functions. Okay, so for one variable case, everything is differentiable. Let me first show that. Okay, so for example, check that f of x, y, which was equal to 1 or 0 if xy equals 0, 0 if xy is different than 0, is not differentiable at 0, 0. Okay, but if z equals f of x and f prime x sub 0 exists, then f is differentiable at x sub 0. So for one-dimensional case, having derivatives and differentiability is the same. So let's see how we can write this. So we have f of x minus f of x sub 0. Okay, so that's what I'm trying to write, right? I take this to the other side and I'm checking if I can write it linearly. Let's play with this thing. So these things always come by playing with these things. I have f x minus f of x sub 0 divided by x minus x sub 0, then multiply with x minus x sub 0. Okay. So this is, and I don't want this. I want something like this. I want f prime at x sub 0 times x minus x sub 0. This is what I want. So I write it there. Therefore, I should subtract it. Okay. Minus f prime x sub 0, x minus x sub 0. Okay. For differentiability, I want this side, which is this and this, equal to a linear part. Okay, here is my linear part. Okay, so I have only n equals 1. So the derivative at that point times x minus x sub 0. I have that here, and the other part is garbage. If I can collect them and make it look like this, it will work. So I have f prime x sub 0, x minus x sub 0 plus. So I take this out of parentheses here. I have f of x minus f of x sub 0 divided by x minus x sub 0 here, minus f prime x sub 0 here, x minus x sub 0. Okay, so call this epsilon 1. As x goes to x sub 0, this goes to the derivative. The derivative here I subtract. So clearly, limit x goes to x sub 0, epsilon 1 is 0. F prime minus f prime. Okay, so in one-dimensional case, its derivative exists and it is differentiable at that point. Are the two names, but they are interchangeable. They are the same. In two-dimensional case, we have functions which are not differentiable, but they have derivatives at that point. Okay, so then the question is, how are we ever going to find out if a function is differentiable or not? So fortunately, there is this theorem which makes life easier for us. So how do we know if z equals f of x, y is differentiable at x sub 0, y sub 0? Okay, so we have a big theorem for this. So if partial derivatives of f at x and partial derivative of f respect to y are continuous at x sub 0, y sub 0, then f is differentiable at x sub 0, y sub 0. So if the partial derivatives are continuous, then the function is differentiable, but it doesn't say that if the partial derivatives are not continuous, it's not going to be differentiable because there are examples, there are lots of functions which are differentiable, but their partial derivatives are not continuous. So if you look at this, suppose we are looking at functions of two variables. So suppose this is the world of functions of two variables. Okay, so functions of x and y. Okay, so we have a small portion of this, a very small portion of this. So partial f, partial x, partial f, partial y exists. Okay, and we have a very small portion of this. Partials are continuous. Actually, the picture is very exaggerated. If this is the world of functions of x, y, the ones which have this will probably be only a line like this, very small, and then this part will be only some points on it. But I'm not trying to invent a measure on this space. This is just to understand what we are doing. Okay, so we are not commanding all of the universe. Fortunately, most functions that we deal in our everyday life are nice functions, and they fall here. So most of the time we are doing our calculations here, and we do a lot of great jobs by functions here, and then after a while we get the feeling that we are the emperors of the universe. But you see, once you pass this line, nobody listens to you. We don't have techniques to understand these properly yet. Okay, so that's what we are working on in math department. 100 years later, we'll probably understand a little bit more. Okay, so I think I can give you a proof of this thing. You are not responsible for proofs of this thing, but I just want you to know that these things are not magical things. Okay, they follow very nicely from fundamental things that we did last semester. So let me start the proof here. See if you can convince yourself that everything is nice. So sketch of proof. Okay, so I want you to follow this sketch of proof just like some movie from Disneyland. You are not going to reproduce this, but you see these things follow from, for example, mean value theorem we did last semester. Okay, so we have this function x sub 0, y sub 0, and we have this point x, y here. Okay, so x, y is actually x sub 0 plus delta x, y sub 0 plus delta y. So I move a little bit to the right. So this is x sub 0 plus delta x. I keep y. And then I move up by delta. So I'm trying to understand the difference of this. So remember, now suppose x is a vector. So I'm trying to understand the difference between the value of the function here and here. For differentiability, I need this, x, y minus f of x sub 0, y sub 0. Okay, so I do something similar here. You see, I divide it by something and multiply it by something. I still didn't like it. I said I want this one, so I wrote it. But since I wrote it, I subtracted this. So I'll do something like this here. I have this function here, f of x. Now I'll write it as x sub 0 plus delta x, y sub 0 plus delta y. From this function, I subtract the value of the function at this point, f of x sub 0 plus delta x, y. Since I subtracted this, I'll add it, f of x sub 0 plus delta x, y. Okay? And then I have this one here, which I didn't write so far. I have f of, this one is y sub 0, right? Y sub 0, okay. And this is y sub 0, f of x sub 0, y sub 0, okay? So I just subtracted and added the same thing. The value of the number I add and subtract is the value of the number here. Okay, so if you remember last semester, the first few chapters, you remember that there was mean value theorem. Now apply mean value theorem. Mean value theorem. So maybe I just write MV, that's always written as mean value theorem. Okay, the value of the function here minus the value of the function here is equal to the derivative of the function somewhere in between times the length of the interval. Okay, so there is some number here, C1. So what is C1? Okay, so C1 is x sub 0 plus delta x, C1. C1 between y and y sub 0. Some C1 between y and y sub 0. Okay, such that the derivative, now the derivative is, you see, I'm keeping the first number fixed. The function changes only with respect to the second part. So, okay, so I write fy derivative. The first part doesn't change. This is only a function of the second variable. I evaluate that C1. Times, I have to multiply this with the length of the interval. The length of the interval is delta y. Delta y is y minus y sub 0. So now I look at this one. Here you see the second parameter is not changing. This is a function of the first parameter only. So I have a one parameter function. I apply mean value theorem to it. So there is a point somewhere here, C2 y sub 0. Okay, here some C2 between x sub 0, x and, oh well, this one is x and x sub 0. Okay, just somewhere here. So I have fx x sub C2 y sub 0 delta x. Okay, so I wrote this. This one is equal to this. This is still not I want. So I'll do the same thing. I'll immediately write what I want. Then I'll subtract it. Okay, I want this to be okay, since I wrote it in this order, fy evaluated at x sub 0, y sub 0, delta y, plus fx evaluated at x sub 0, y sub 0, delta x. This is what I want. Okay, so now I'll subtract it. Okay, I'll subtract it in the following form. So I have this fy x sub 0 plus delta x c1. I subtract this one, fy x sub 0, y sub 0, delta y. Okay, so I paid my duty here. I added this and I subtracted it. Plus, I'll do the same thing here. I have this nice person here. I subtract from it what I added, delta x. Okay, now I have the equality. Okay. By applying mean value theorem, I obtained this. This looked like what I wanted, but it's not exactly what I want. I want this one, so I write what I want and I subtract what I want. I just regroup these things. Now call this epsilon 1. Call this epsilon 2. Now limit as delta x, delta y go to 0, 0, or xy goes to x sub 0, y sub 0. Epsilon 1 and 2, okay, let's say epsilon j is equal to 0 because partial derivatives are continuous. Okay, can you see it? Since this function is continuous, I can take the limit operation inside. As the delta y goes to 0, this part goes to 0, this interval goes to 0, so this c1 goes to y sub 0, okay? Because c1 is always in between. Here, when delta y goes to 0, this shrinks, and c1 is always somewhere in between, so in the limit, c1 becomes y sub 0. So this person becomes derivative of f respect to y at x sub 0, y sub 0. Well, I'm subtracting it, it's 0. So similarly here, partial derivatives are continuous. The limit then goes inside, and epsilon 1 and epsilon 2 go to 0. So if the partial derivatives are continuous, it shows up in the error term, and the definition of differentiability is satisfied. And everything hinges on this one, mean value theorem. So that's why last semester we told you that even though it is totally trivial by the time we develop it, it is a very deep theorem. Deep theorem means that it surfaces here and there. Every time there is a crucial problem, that deep theorem comes out and saves you the day. And how did we prove mean value theorem? If you look at how we proved it, we started that was proved using Rolle's theorem. Rolle's theorem was proved using some obvious observation that if there is a maximum point, the derivative is 0. Okay, so everything goes down to the very fundamental things we did in the first chapters of calculus. Okay, so this is just to show you that this thing is not magical. It follows from very basic concepts. So in our real life, going back to real life, we will be dealing with rational functions, polynomial or trigonometric functions. And these functions, wherever they are defined, they are continuous. Their partial derivatives are continuous. So mixed partials will be the same because, again, for the equality of the mixed partial, you have a proof similar like this. You show that those two mixed partials are the same. So everything depends on saying that if you use nice functions, life will be nice. It's just like having good friends. If you hang around with good friends, you'll have a nice function. If you have bad friends, then nobody knows where you'll end up. Okay, so now what do we do next? Okay, I gave the definition of differentiability. I did this. Okay, so we use this. Now at this point, we start talking about linearization. Linearization is a way to show how powerful these techniques are. Okay, now that we have computers or even smartphones, which can do almost everything, these calculations are not necessary for everyday life, but just to demonstrate that we are doing something nice. Okay. Note that the equation of the tangent plane gives a linear approximation for the function at that point. Okay, so when we talk about linearization of the function at this point, we mean the equation of the tangent line, tangent plane, or whatever dimension you are in, written at that point. Later on, if we do Taylor series, a function will have a Taylor series, and the linearization is the first linear terms of that Taylor series. So the function is equal to a constant, the value of the function at that point, plus a linear term, plus a quadratic term, plus a cubic term, etc., up to infinity. And if you take just the linear part, you are doing a linear approximation. If you take linear plus the quadratic part, you are doing a quadratic approximation. The nice thing at that point will be that we will have a tool, namely Taylor's theorem, which tells you how much error you are making as an upper bound. If you know exactly how much error you are making, you are not approximating the function. You exactly know the value of the function. But Taylor's theorem will tell you that if you use this part, for example, in our case, if you use the linear part, the error you make will not exceed such and such number. Okay? But at this point, our tools, the ones that we developed so far, does not tell us any idea about the error. So we'll just do this as a preparation for Taylor series. Okay, so say z equals f of x, y is differentiable at x sub 0, y sub 0. An equation for its tangent plane at x sub 0, y sub 0, f of x sub 0, y sub 0 can be given as derivative of x at x sub 0, y sub 0, x minus x sub 0 plus f of y, x sub 0, y sub 0, okay, y minus y sub 0. Okay, so here, of course, I take these. So this thing should be, okay, I'll also put f of x sub 0, y sub 0. So this is an expression in L, x, y. Okay, so if xy is x sub 0, y sub 0, these are 0. You get exactly the value of the function. If you move a little bit, they contribute something to the function. And of course, since it is differentiable, we have an error term here. Okay, so we are not mentioning the error term here. So I think I have some examples here, but before the example, let me look at if I missed something. Well, this is all I have to say before the example. Okay, so remember that this looks like the linearization of a function of a single variable. There we have only one derivative, so you don't have this derivative. So forget about y. X is your parameter, okay? So the tangent line is a one parameter stuff. So depending on this parameter, you go to the value of the function and then you move in the direction of the tangent line, okay? So this is approximating it. And this is something that we can visualize. Obviously, algebraically linear approximation exists for all dimensions, but we cannot draw the picture. So now to show you that this thing actually works wonder, I'll have an example here. Consider this function fxy equals x to the 4 plus x cubed y square minus y cubed. Okay. So we want linear approximation at 2, 3. Okay. So again, when we come to, I think we'll come to that at the end of the semester, when we come to Taylor series, we are saying that write the Taylor expansion of this function around this point. Okay, so the first term will be the value of the function there, which is 61. And the second term will be a linear term. Then we have quadratic, cubic, etc. That linear term is the tangent plane here. Okay, so here f2, 3, I calculated this to be 61. Then I have derivative of x respect to derivative of f respect to x is, okay, so I'll just write these things and you check if I'm writing correctly. Then, of course, for the linear approximation, I want to evaluate the derivative at that point. So I just put 2, 3 there. Okay, so my calculator gave 140. Then I have fy xy equals, so let me just 2x cubed y minus 3y squared. Then I put 2, 3. And I put this, it is 21. Okay, so linear approximation x, y is equal to 61. Okay, so I'm following this one. 61 plus 140 x minus x sub 0, which is 2, plus 21 y minus 3. Okay, so this is your linear approximation, and I didn't simplify this any further because most of the time linear approximation is useful in this form. Linear approximation is generally used to approximate the value of the function around this point. So I move a little bit away from 2, I move a little bit away from 3. So that will be reflected very easily in this notation. So that's why I don't multiply these and simplify it. Okay, so for example, we calculate L 2.1, 3.1. So if we are doing this on your computer, and if your computer is using Turkish notation, you must put commas here. Okay, so 2, 1. Okay, so this is calculated to be 77.1. And since we can calculate the function as a polynomial, I'll do that. This is 78.6. Okay, not bad. But you see, this becomes impressive when we have things like this, 2.9. This is equal to 72.90. If I do this, 2.9, this is 72.94. I'll even be a little bit close to the point, L 2.01 and 2.99. So I'm almost there. And linear approximation gives me 62.1900. The actual value of the function, which again you can calculate since it's a polynomial, 0.1299 is equal to 62.1904. Okay, so you see, as the point approaches to x sub 0, y sub 0, the error term goes to 0 very fast from the definition of differentiability. Okay, so you see that when we are getting closer to the point, to this point getting closer to this point, the error we are making is at this stage. Okay, so this is just to convince us that it is working. As I said, at this point, we don't have an error estimate for this function, but later on we'll have very strong tools for error estimation. Okay, so there is one more thing about differentials. So let me very briefly talk about differentials. So differentials at the level of calculus is another fancy name for linear approximation. Okay, except that with instead of delta x you write dx, instead of delta y you write dy. Actually you are introduced to this notation because later in third year, if you start doing differential geometry, then you see that these things have a different meaning. They work like we show you how they work, but their meaning is totally different. So I'll just pretend that we are doing this within calculus. So differentials in calculus. So let me attempt to draw a picture. So we have, again, a surface here like this. And at this point, we have the tangent plane. Okay, so this is the tangent plane. So this is tangent plane. And this is the graph of the function. Z equals f of x, y. And at this point, say, this is x sub 0, y sub 0. Okay. So suppose you move by delta y here in this direction, Now we denote it by dy. So I move too far. Okay, so let me make this larger. Okay, so I have here. So I have the value of the function here, and when I go here, okay, so the value of the function here, and suppose it cuts the surface here. So this difference here, okay, is delta z. The difference between the value of f at x sub 0, y sub 0, and the value of f at x sub 0, y sub 0 plus delta y is delta z. Okay? So that's our usual notation. Now when we introduce this, we look at the difference between, so we write dz for the difference between f of x sub 0, y sub 0, and L of x sub 0, y sub 0 plus delta y. Okay? Because at this point, you see, at this point, the tangent equation of the tangent plane and the function has the same value. Then the tangent plane goes linearly, the surface goes curved. Okay? Normally, forget about this. Normally, when you move a little bit, say in one direction, you choose how much the function changed. Instead of checking how much the function changed, if you choose how much the tangent plane, how much the linear approximation changed, you call it dz. Okay? So you see that as we approach to x0, y sub 0, these two values get close to each other. So dz is actually how much the linear approximation changed. Okay? So the rules for this thing are, so how it works. The differential of a function is defined. So this is how we define the differential. Derivative of this with respect to x times dx. So we interpret this as delta x because x and y are moving in the parameter space. Okay, so this part is only what happens up plus fy xy dy. And if you have more parameters, you keep going like this. If you have one parameter, this is what we did in last semester calculus, differential of f of x. Okay, so remember, differential of f of x was f prime x dx. Okay, so we wrote this notation, and we only used it, if you remember where we used it, we only used it in change of variables in integration. Okay, so we'll use again this in change of, but we will not tell you that. You will not learn it until you grow up. This will be used in change of variables of multiple integrals, because a differential is actually what you integrate. Okay, so remember that when we have integrals, so this was used in integral, you have f of x dx. Okay, so we said you integrate this, so let me write it over here with a different color. So, but you don't tell anybody that I'm telling you these things. So in calculus, since you are still young, we tell you that you integrate this function, but since you are stupid, you may forget that x is a parameter, write x here, okay? So this is a lie. Actually, we are integrating, so the actual thing is, we are integrating this whole thing. This is an object in mathematics called a differential form. Here we have only one parameter. You integrate this on a space, or in this case, an interval, okay, throughout the line. So you see that these two things, when they see each other, they give you a number. Okay, that's the theory of integration. And in higher dimensions, we have higher dimensional differential forms. And when they see a higher dimensional space here, they give you a number. Okay, in that setup, this differential has a different meaning, but we don't want to talk about here because it's the set of all functions on the tangent plane, and it has a different behavior, and it's, we can explain that to you in one class or two class, but then you will not use it in calculus. So that's why we prefer to say that this is how it works. Okay? So the only thing that you have to remember from differentiation is this one. Okay? And in practice, for these things, you put delta x and you put delta y. So there are some artificial problems in the book. The volume of something is given by 2 parameters. Okay? So how much the volume is changing. So this is how much the volume is changing when you change one parameter like this and the other parameter like this at a certain point, at a certain time. So the parameters were 5 and 7. You increase 7 a little bit, okay, like this. You increase x a little bit, like this. So how does the whole thing change? Okay, so this is the only way where we will use. So if you just rephrase the problem, you will see that it's just a linear approximation. Because it will give you an approximate change. It's not going to give you exact change. If you want the exact change, you just calculate the function. Okay, so that is, I think, all you want to do with this linear approximation stuff. Let me check if I forgot to tell the story of something. Okay, so I think we did all of these things. So the next thing is chain rule. So let me start doing the chain rule. But before that, do you have any comments? Any questions? Sen ne gördün rüyanda? So in your sleep, you saw Stuart, and Stuart saying, don't sleep in my class. After all, this is his book. Okay, so we talked about a lot of things, but there is only one little idea, taking derivative of a function with respect to one parameter. And you do this by keeping the other parameters fixed. Okay, so this is the only technical tool that we mentioned. Then all the other stories we told are about the geometric meaning of this. There's only one geometric meaning that we are interested in. It's the tangent plane. Well, since we can draw pictures only when there are 2 variables, the third variable is in R3. So I'm giving all geometric intuition in R3. So you write the equation of the tangent plane using these partial derivatives. If the function is nice, this tangent plane approximates the function very nicely. In technical terms, nice means differentiable. Approximates means that you have this epsilon times delta x plus those technical expressions. Okay, so that's all. We just take derivatives.
In the differential semi-calculus part, how does the dimensions suit?
In what, here?
Respect the volume?
Here or here?
Below.
So here in higher dimensions you will have fxy dx dy. Okay, so you will be evaluating this on a surface, on a, let me say, region. Okay, so this will be your region. And when you do change of variables here, we'll do it in the next chapter. When we are doing change of variables here, there's a complicated looking formula. But I'll tell you that if you do it by multiplying differential forms, the change of formula is just mechanical. You just multiply things according to a rule, which we don't tell you, but I'll tell you. Okay. So this is how it goes to higher dimensions. You multiply these, you get volume. This is volume in 2 dimensions. In 3 dimensions, you get dx, dy, dz. Okay? So, you see, calculus is easy. Actually, we did everything in calculus last semester when we learned how to take derivatives. Okay, so now we are taking derivatives of things which look complicated, but we are not dealing with their complication. If there are 5 parameters, we fix 4 of them. So this is, again, derivative of last semester functions. Okay? Except that now we tell lots of stories, put this inside a story, and we pretend that we are doing something very complicated, but we are just taking derivative of one variable. Okay, now in one variables we had chain rule. So the problem comes again, what is the chain rule here? Remember that last semester we insisted that you don't cancel the x's, you don't cancel dy's. Okay, we'll allow you to do it just because you are too young, too inexperienced. The reason was in one dimension, in one parameter case, dx's and dy's behave as if they are cancelled. You can cancel them safely. The result is actually correct. But in several variables, they don't cancel. Okay, so to remind you that they are not canceling, we use curly brackets. But again, if there is curly dx and there is curly dx here, one is tempted to cancel them. They don't. They don't means that, of course, nobody is holding your hand. You can cancel them, continue your calculations. This is algebra, okay? So it will give you a number 17. But that 17 has nothing to do with the number you are trying to find. Okay, so let's now start with the chain rule after this warning. Now we have a function. Let me again do this with two variables because you see there is also always a difference between passing from 1 to 2 variables. And then from 2 to 3, you just add more symbols. The ideas are the same. So I'll do this for 2 variables. We have a function which depends on x and y. Okay? So f is differentiable. Okay, so here's the crucial thing. So this means that partial derivatives will reflect the behavior of the function. So in particular, I can write the definition of differentiability. F will be given as partial derivatives, dot product with points, etc. Okay. X is a function of t. Y is a function of t. These are, again, differentiable. Now here differentiable means that their derivatives exist. Okay. So z equals f of x of t, y of t makes z a function of t. So obviously the question is then what is derivative of z with respect to t? Okay, so this is the question. So what we do is the following. So, okay, these things, we have to invent some. First of all, let's write this differentiability, then maybe we can do this without inventing new notation. If you don't invent new notation, it will be crowded. If you invent new notation, you have to remember it. So there is always conservation of pain. So what is the z over dt? If it exists, it is limit delta t goes to 0 of z of t plus delta t minus z of t over delta t. Okay. Now the nice thing is I can write this using differentiability. Okay. Z is differentiable. So z of t plus delta t minus z of t is, okay, so let me see how I can write this. So this is f evaluated at derivative of f with respect to x evaluated at x of t, y of t, right? Times here, okay, so this is x of t plus delta t minus x of t. So that's why we invent notation. I want to call this delta t, but anyway, let's continue. Now that we started, f of y, x of t, y of t times y of t plus delta t minus y of t. And now I have to write the error term plus epsilon 1 times this thing, x of t plus delta t minus x of t, plus epsilon 2 times this thing, y of t plus delta t minus y of t, where epsilon 1 and epsilon 2 go to 0 as delta t goes to 0. Okay? So now let's see, I'm trying to calculate this. I have to divide everything by delta t. So let me show you what happens when I divide everything by delta t here. Here I'll divide this is a product, so I'll divide this by delta t. Here I'll divide this by delta t. Here I'll divide this by delta t, and this by delta t. Now, derivative of z with respect to t exists if this limit exists when delta t goes to 0. So I managed to write this thing in more complicated term with the hopes that I can understand the terms, each term, easily. So I check if the limit of the right-hand side exists as delta t goes to 0. Okay, so there is no delta t here. This is constant as far as delta t is concerned. This limit exists. So again, let me use this. Okay, so this thing goes to x prime t as delta t goes to 0. This thing goes to y prime t. Now here again, this is what saves me. This again goes to x prime t, and this goes to y prime t. Okay. Now what happens to this one? So here you see I'm taking derivatives, limits as delta t goes to 0. As we said a minute ago that as delta t goes to 0, these two error terms go to 0. Okay, so now I have the chain rule. Okay, so we have our glorious chain rule. So derivative of z with respect to t is equal to, okay, so let's write it like this. Derivative of f with respect to t, because z is this. This is equal to derivative of partial derivative. Okay, so this is partial derivative of f with respect to x. Then I took the derivative of x with respect to t. Derivative of x with respect to t. I'm deliberately writing this in this notation to come back to what I said about these dx dt's not canceling. Okay? And then this part is derivative of f with respect to y times dy dt. Okay, so this is our glorious chain rule. Okay, so you see, there, if we cancel this like we did last semester, derivative of f respect to t, I cancel dx's here, I cancel dy's here, I get derivative of f respect to t here, derivative of f respect to t here. So this thing is equal to twice itself. Therefore, this thing is 0. So all derivatives would be 0. But they are not. Okay. So this notation does not cancel. It has a different meaning. Okay, so let's continue from here on Thursday. On Thursday, you will have a surprise quiz about, I think, linearization. I prepared the question, but I forgot. But don't tell anyone, it's going to be a surprise quiz.